6b. Forces. 6.5 Summing forces. Everyone intuitively understands that push, or an object to be moved. Pushes and pulls belong to the class of physical phenomena called forces. All matter is held together by forces. Matter exerts forces and has forces imposed on it. You may associate the word force with human activities and machines. Immense man-made forces are required to lift a space shuttle into orbit or to nudge an oil supertanker against a pier. However, these forces pale in comparison to the inconceivably powerful natural forces unleashed by a hurricane or the eruption of a solar flare. See Figure 6.7. You also consciously and unconsciously employ small forces in your daily life routines. When you press the keys on cell phone, breathe, swallow, walk, sit, pull a sweater on, or write. Forces have magnitudes and direction. They can easily be represented by vectors. Forces, for example, obey vector addition rules. Multiple forces can also act on an object simultaneously. In order to describe and predict how a force will affect an object's motion, we must know where the force is being applied. We will address that question later, but for now, we will assume that the object on which forces are acting is a particle with no physical size and that all forces act on the same point. In later chapters dealing with circular motion and torques, we will consider what happens when forces do not act on the Serre point on an object. Even though forces can be pushes or pulls, we will diagram forces as only pulls on the point of application of the force. This convention will help you avoid confusion when solving problems. The SI-derived unit of force is the Newton, N. The effects of simultaneous forces acting on an object are of primary interest in physics. Therefore, we will assign the vector sum of simultaneous forces the symbol. Sigma F equals F1 plus F2 plus F of N. The Greek capital letter sigma is the mathematical summation symbol that stands for the sum of all terms, represented by the variable following it. 6.6 Balanced and unbalanced force sums. Forces do not always cause a change in motion. In Figure 6-8a, two people are pushing on a refrigerator equally hard, but in opposite directions. As you would expect, no motion occurs. If the sum of all forces acting on an object is zero, then we say that the forces are balanced. Balanced forces cancel each other. The following mathematical expression is true for balanced forces. Sigma F equals 0, sigma Fx equals 0, and sigma Fy equals 0. In other words, when the force sum on an object is 0, the sums of the forces x and y components are also 0. In Figure 6-8b, one man has a cramp in one arm, so he cannot push as hard as the other man. The refrigerator moves toward the man who pushes less. Unbalanced forces change an object's state of motion. A pair of balanced forces on an object is represented by two vectors with the same magnitude but opposite directions. When these vectors are summed, they add up to a zero resultant vector. If two forces act at less than 180 degrees to each other, you can use either the geometric addition method or the mathematical technique of vector resolution to determine the vector sum. Three or more forces acting on an object may sum to zero, but it is more likely that there will be a net resultant. The presence of unbalanced forces means that the force vectors do not cancel. Example 6-1 shows how unbalanced forces are used to move a ship in a desired direction. 6.7 The Equilibrant Force. When a force sum is 0, then any one of the contributing forces exactly balances all of the others. A force that balances one or more other concurrent forces is called an equilibrant force. See Figure 6.11. The equilibrant of a set of unbalanced forces is a vector having the same magnitude as the vector sum of the other unbalanced forces, but pointing in the opposite direction. In equation form, this means F equal or sigma F other, where F equal is the equilibrant force and F other are all the other unbalanced forces acting simultaneously on the object. You can use the equilibrant concept to determine an unknown force. If the sum of all forces on an object is 0, then any unknown force must be the equilibrant of all of the known forces. The weight, Fw of an object is the force of gravity acting on it. This is a common force that must often be considered in mechanics problems. Example 6-2 demonstrates how weight can be an equilibrant force. 6.8 types of forces. Gravitational force. All forces can be classified as either fundamental forces or mechanical forces. The fundamental forces are inherently part of the atomic building blocks of matter. Scientists have identified 4 fundamental forces in the universe, from which all other forces are derived. Of the 4, 2 were discovered as recently as the 20th century. The first to be recognized and mathematically described by Newton during the 17th century was the gravitational force. This long-range force is proportional to the masses of the interacting objects and exerts its influence over theoretically infinite distances. It is the dominant force that organizes the structure of astronomical bodies, controls the motions of planets around the sun, and governs the celestial processes of the universe. All objects exert gravitational force on all other objects. You will study the effects of gravitational force in association with nearly all mechanics topics in Units 2 and 3, as well as its importance to modern physics in Unit 6. Electromagnetic force. The existence of magnetic and electric forces had been known for millennia and studied to some extent in the 17th century. But these forces were not recognized as 2 components of the same fundamental force until the mid-19th century, when James Clerk Maxwell formulated the unifying theory of electromagnetism. The electromagnetic force, as it is now called, is also a long-range force. You have seen long-range electrostatic discharges in the form of lightning, and the Voyager space probes have detected the sun's magnetic field billions of miles from its source. The electromagnetic forces also act at very short distances. They are responsible for chemical bonding and other interactions among atoms and molecules. The electromagnetic force governs the fine structure of matter because it determines many of the physical and all of the chemical properties of substances. You will study electric fields in Chapter 19 and magnetism in Chapter 21. Combined electromagnetic theory will be studied in Chapter 22 and in Unit 6. Strong and weak nuclear forces. Early in the 20th century, 2 short-range fundamental forces or interactions were discovered during the development of the quantum model of the atom. These forces act only over very short distances, less than a few femtometers, 10 to the power of minus 15 meter, which is comparable to the diameter of protons and neutrons in the nuclei of the atoms. Thus, they are called nuclear forces. The strong nuclear interaction force binds together the particles forming the nucleus, while the weak nuclear interaction force is involved in several modes of nuclear decay. You may study these 2 nuclear forces in advanced physics courses. 6.9 Classification of forces. Prior to the last century, forces seemed to be easily classifiable into those that could act through space without physical contact, and those that could be transmitted only through physical contact between objects. Non-contact forces. In one model, gravitational and electromagnetic forces are called action at a distance forces, to emphasize that no physical contact is necessary for transmission of the force. This model assumes that each kind of force is a property of the associated matter, which can somehow be exerted at a distance without requiring physical contact. Another approach to explaining non-contact forces is the field theory. This theory proposes that the gravitational influence of matter and the attraction or repulsion of magnetic or charged particles are properties of the space surrounding the matter, the field. The matter exerts forces on other massive magnetic or charged particles when they are placed in their respective fields. The development of quantum mechanics after World War II produced yet another model that tries to account for all of the fundamental forces. It suggests that virtual particles are exchanged between matter with like characteristics. The exchange of the virtual, non-material carrier particles supposedly creates the force. Virtual particles have been identified for the electromagnetic, photons, and nuclear forces, gluons. But no particle has yet been identified that carries the gravitational force, graviton. You will study some aspects of these three force models in later chapters. Contact forces. As mentioned earlier, the electromagnetic force is responsible for both the structure of the atom and the chemical bonding between atoms. The electromagnetic forces in the electron orbital structures of atoms can either attract or repel other atoms. Most atoms have some tendency to attract and hold on to nearby atoms, but no two atoms can occupy the same space at the same time. When aggregates of atoms, any kind of matter, are forced together or pulled apart, the particles exert forces between each other. This gives rise to the concept of contact, or mechanical forces, forces that are transmitted only by physical contact between objects. Contact forces include tension or tensile forces, forces that tend to pull things apart; compressive forces, forces that tend to push things together or to crush; torsion, twisting forces; friction, forces that oppose motion between two objects in contact; and shear forces, forces that tend to cause layers within matter to slide past one another. Mechanical forces and the gravitational force will be the forces of primary concern in Units 2 and 3. According to Scripture, the advent of forces in creation must have been during the very first instance of time, Genesis 1:1. All four fundamental forces appeared as matter was brought into existence: gravity from the matter itself, electromagnetic forces in the chemical bonds between the atoms of the matter, and the nuclear forces that held the atomic nuclei together. The material world continues to exist as a direct result of God's providence in sustaining these forces. For by him, Jesus, were all things created that are in heaven and that are in earth, and by him all things consist. Colossians 1:16-17. 6.10 Measuring forces. Forces may be measured using a variety of instruments. A typical force measuring instrument in a high school laboratory is the spring scale, shown in Figure 620. The displacement of the spring, indicated by the change in position of the pointer from 0, is directly proportional to the force applied to the spring, so the scale is calibrated in appropriate increments to indicate the applied force. Materials engineers use a type of force sensing detector called a load cell to measure large forces applied to material samples. It consists of a crystalline substance, such as pure quartz, that produces an electrical signal when the crystal is squeezed by the applied force. Forces may also be inferred using instruments such as pressure gauges, ballistic pendulums, and accelerometers. These and other instruments will be discussed later in this course. In the classroom, a force table shown in Figure 622 demonstrates the addition of force vectors. When the attachment ring is stationary directly above the center of the table, the applied forces are balanced. With this apparatus, the equilibrant force can be determined directly by finding the weight of the suspended mass generating the force.